Friends, today we shall discuss the equal criteria for stability. We have studied that to analyze the stability of a power system, we have to solve swing equations, and solution of swing equations is through a numerical technique, and it is a time consuming process. The equal criteria of stability is very powerful tool to understand the basic concepts of stability. However, as we will see that this criteria has its limited applications. Now, today in our study we will establish this basic concepts pertaining to equal criteria, and we will analyze considering one machine swinging with respect to the infinite bus. Then we will develop the equivalent of one machine infinite bus system of a two machine system. Then we will study the applicability of equal criteria, under what circumstances or for what systems this criteria is applicable and what are its limitations. Then we will illustrate the application of this criteria considering two examples, a sustained line fault and second a line fault with subsequent clearing. The equal criteria of stability is a graphical method for determining whether the system is stable or not. That is, in any stability studies, our primary requirement is that for given operating condition and for a given disturbance, whether the system is stable or not. Many times we are interested in knowing if it is stable, how much stable it is and what is the stability margin. This information we can get by plotting the swing curve, but as I told you that the computation of swing curve is time consuming, and for simple system, for a two machine system or a one machine connected to infinite bus, we can obtain this information by applying a graphical method, and that method is the equal area criteria. Now, when this criteria is applicable, its use wholly or partially eliminates the need of computing swing curve and thus saves considerable amount of time. I am emphasizing here that it eliminates the computation of swing curve wholly or partially. Okay? That we will see actually when we attempt some example. This criteria is applicable to any two machine system for which commonly made assumptions are applicable. Right? We have studied the commonly made assumptions for analyzing the tangent stability problem, and when these assumptions are applicable, this can be applied to any two machine system. Now, first we will mathematically establish the equal area criteria of stability. To establish, we start with the swing equation of a machine. Here we are considering a machine connected to the infinite bus. Infinite bus is one which can be represented by a constant voltage source. Its internal impedance is 0 and its inertia is infinite. Now, you multiply this both sides of this equation by a term 2 delta d delta by dt. When we multiply both the sides by this term 2 times d delta by dt, we get equation in this form: 2 times d2 delta by dt2 into d delta by dt equal to 2 times Pa by m d delta by dt. Now, this left hand side of this equation can be identified as derivative of d delta by dt square. you look at very carefully, that is if you take this term and find out its derivative, you will get the term 2 times d2 delta by dt to d delta by dt. Okay? And right hand side we are writing as it is 2 times Pa by m d delta by dt. Okay? The next step is you multiply both sides of this equation by dt, and we are getting differentials instead of derivatives. That is, when you multiply both sides of this equation 5.3 by dt, it becomes a differential, that is d of d delta by dt square equal to 2 times Pa by m d delta. Okay, which is written here actually as d of d delta by dt square 2 times Pa by m d delta. Okay. Now you integrate this equation 5.4, integrate it. When you integrate, you will get d delta by dt square equal to 2 by m integral Pa d delta. This integration we are doing over certain range of delta, that you start with initial value of delta naught, delta equal to delta naught, and do to some value of delta. I am just putting it general, there is delta naught to delta, I am not specifying what should be the value of delta here. Now from this equation 5.5 we can write d delta by dt equal to square root of 2 by m integral Pa d delta. The limits are implied. Okay. Now we look at this equation and we know that the condition which indicates the stability of the system is that d delta by dt should be 0. That is, a system starts when it is perturbed, right, with the initial value delta naught, and when delta increases, it will attain a maximum value, then start decreasing. That is the condition of stability. It means that when it goes to maximum and start decreasing, that maximum point, at that maximum point d delta by dt is 0. Therefore, the condition to indicate the stability is that d delta by dt should become 0. Now for this d delta by dt to become 0, which is the condition to indicate the stability of the system, our requirement is that the integral of Pa d delta from an initial value of delta equal to delta naught to some value delta m should be 0. That is, if I plot the area under the curve Pa, the accelerating power, starting from initial value delta equal to delta naught to some maximum value delta m, and in case the area under this curve is 0, right, then at the value delta equal to delta m, the d delta by dt will become 0. Right. Now this I will show here in this diagram. This is the power angle characteristic of the system. This shows the mechanical input line. Now in this diagram I am simply showing that suppose initially system was operating at delta naught and the power angle characteristic applicable for the initial operating condition was not this but something different. The moment fault occurs on the system, the operating point has shifted from this point to this point. Okay. Then delta will increase from operating from the point A on the power angle curve Pe. The initial acceleration is given by this, or initial accelerating power is given by this line. This is the initial accelerating power. Okay. Therefore, rotor accelerates. When rotor accelerates, the delta will increase, speed increases, then delta increases. And now when it reaches the point B, right, the accelerating power becomes 0. Now at this point, what is the rotor speed? the rotor speed is more than the synchronous speed, because from when it is traversed from this point A to B, the rotor is accelerated, gained some kinetic energy, it has gained some extra speed over and above the synchronous speed. Therefore, at this point the rotor will not stop, it will continue to, the angle will continue to increase. Now, the moment it crosses this point B, we see that the accelerating power becomes negative, that electrical power output becomes more than the mechanical input. Therefore, now the rotor will be subjected to retardation, and when it reaches a point C, if suppose whatsoever the kinetic energy it has gained, if it is returned back or is lost, then at point C the rotor will again attain a speed equal to synchronous speed. And therefore, for the system to be stable, the rotor will swing from delta naught to delta m, and the area under the accelerating power. Now, here the accelerating power is obtained by subtracting, therefore, here I can say that accelerating power curve is given by this difference, okay? And therefore, this area should be 0. Now, for this area under the accelerating power curve to become 0 requires that this positive area, we call this as a positive area because accelerating power is positive, this is called negative area, accelerating power is negative. Therefore, these two areas should be equal, and this is what is known as the equal area criteria of stability. Now, this equal area criteria of stability can also be interpreted in terms of the kinetic energy gained and kinetic energy lost, right. Now, we know actually that suppose a rotor is subjected to a torque T, and when it swings from delta naught to delta, the work done on the rotor is equal to, or work done by the rotating body is equal to T into d delta. This is actually when the delta is small, and you integrate this expression from delta naught to some value delta, then this becomes the work done when the rotating body accelerates, okay, or decelerates. It depends upon the situation. And hence we can say that the area A1 represents kinetic energy gained by this machine, or I can say this area A1 is proportional to kinetic energy gain. There has to be some proportionality constant. I can't say that A1 is in joules or megajoules or so. It will depend upon what is the unit which we attach to it. Now, the derivation is, which we have seen just now, is considering a machine connected to infinite bus. Now, suppose you have two finite machines, a problem that of a synchronous generator supplying power to a synchronous motor through a transmission line. Then this two finite machine system can be replaced by an equivalent machine infinite bus system. This derivation is very straightforward. We take the swing equation of machine 1, d2 delta 1 by dt2 equal to Pa1 by m1, that is Pm1 minus P1 by m1. Then we take the swing equation of second machine, d2 delta 2 by dt2 equal to Pa2 by m2, that is Pa2 is Pm2 minus Pe2 upon m2. Okay. Now, suppose we define here the relative angle between the two machines as delta equal to delta 1 minus delta 2. Now, whether these two machines are going to remain in stable condition or become unstable is going to be determined not by delta 1 and delta 2 individually, but the difference between these two angles delta 1 and delta 2. In case this difference right remains within certain limits, system will continue to be stable, and therefore these two differential equations which we have written, right, if we can be written in this form, that is, you can subtract these two equations, you will find that d2 delta 1 by dt2 minus d2 delta 2 by dt2. Okay. This difference can be written as d2 delta by dt2, because delta 1 minus delta 2 is delta, and on this right hand side you have Pa1 by m1 minus Pa2 by m2. We can multiply both sides of the equation by this product m1 m2 or m1 plus m2, and we may get the expression in this form: m1 m2 or m1 plus m2 d2 delta by dt2 equal to m2 Pa1 minus m1 Pa2 or m1 plus m2. Okay. Now, if we replace Pa1 and Pa2 by Pm1 minus P1 and Pm2 minus P2, we get this expression. That is, I have put here in this expression wherever you had Pa1, Pm1 minus P1, Pa2, Pm2 minus P2, and then simplified. In this we find here that we can write this as m1 m2 or m1 plus m2 d2 delta by dt2 equal to m2 Pm1 minus m1 Pm2 divided by m1 plus m2. That is, in this term we have the inertia constants and the mechanical powers, while here in this term we have inertia constants and electrical powers P1 minus P1 and P2. Okay. Now, this equation may be considered to be the swing equation of a machine connected to infinite bus, where the equivalent inertia constant is m1 m2 or m1 plus m2. The equivalent mechanical input is given by this expression, and equivalent electrical output is given by this expression. Therefore, we can say that this expression written as m times d2 delta by dt2 equal to Pa, Pm minus P, where Pm is given by this expression, Pe is given by this expression. You can say that Pm is the equivalent mechanical input, P is the equivalent electrical output, and the equivalent inertia constant is m1 m2 or m1 plus m2. Now, at this point you can understand that the equivalent inertia constant is as if we are connecting two resistances in parallel to find out the equivalent resistance. Suppose you have two resistances R1 and R2 and you put them in parallel, the equivalent resistance is R1 R2 or R1 plus R2. Therefore, this is the equivalent inertia constant is primarily determined by, or is going to be closer to the smaller one. That is, suppose I put m1, m2 m plus m2 the values. If m2 is large as compared to m1, okay, then when you find out the value, let us say, I am just take example, take just values actually. Let us say m1 is 5 and m2 is say 50. What will be the resultant? It is going to be less than 5, but it is closer to 5, not closer to 50. Therefore, the equivalent machine will have the inertia which is less than the inertia of a smaller machine, or inertia of a machine which has a smaller inertia constant. Now, here at this stage, to illustrate the application of equilibrium criteria for analyzing stability of a system, I will consider an example. The example we consider is a simple example. Let us consider this example. We have a synchronous generator. Connected to a double circuit transmission line to an infinite bus. We put infinity here to show that it is infinite bus, its inertia constant is infinite. To illustrate the application of equilibrium criteria of stability, what we will consider is that yes, there is a machine infinite bus system. We will consider a fault at the middle of the transmission line, one of the transmission lines at the point P. We will consider a 3-phase fault, a balanced 3-phase fault. Okay. I will consider unsymmetrical faults in my next lecture, because in any system we do come across symmetrical and unsymmetrical faults, and unsymmetrical faults are more frequent in occurrence. Okay. Now, let us assume some parameters. Okay. Let us say x d prime for this system is 0.2, reactance of this transformer is say 0.1, that is impedance is J times 0.1. The transmission line is loss free and its reactance is J times 0.4 times 0. Further, we assume that the infinite bus voltage V is 1.0, and we consider this infinite bus voltage as reference, so that V 1.0 angle 0. This is the terminal of the synchronous generator. We denote the terminal voltage by symbol V t, and let us assume that V t magnitude is given to be equal to 1.0 per unit. And also it is assumed actually that this machine delivers electrical power P e equal to 1.0 per unit. Okay. Now, for this system we will obtain the power angle characteristic for 3 conditions. One is pre-fault operating condition, second is during fault or fault on operating condition. Now, once the fault is there in the system, the fault will be cleared by operating these circuit breakers at the 2 ends of the transmission line, and therefore, the third power angle characteristic which we will obtain is post fault power angle characteristic. Although we are considering a simple system, but this exercise is required to be performed even for a multi machine system. We have to obtain the expressions for power outputs of machines under pre-fault condition, during fault condition and post fault condition. And the approach we are following here will also be applicable for a classical multi machine stability problem. I am using the word classical, means here we will be making those basic assumptions that a synchronous generator can be represented by a constant voltage behind direct axis tangent reactance. Now, with this information given, how to find out the pre-fault power angle characteristic? Therefore, here our primary requirement is that to get the pre-fault power angle characteristic, what we need is the voltage behind tangent reactance. This is not given. What is given is the voltage at the terminal of the machine. Now, we can use this information to compute the pre-fault organization. What is first step is you draw from the one line diagram a reactance diagram. The reactance diagram can be drawn as a voltage source. We will denote this voltage source as E prime. Reactance X d prime. The value of this impedance is given as J times 0.1. The transformer reactance is 0.1 per unit, that its impedance is, the generator reactance is 0.2, not 0.1, 0.2. Transformer is 0.1. These two transmission lines and infinite bus voltage, we denote this as V. At this point, which is the terminal of the synchronous generator, the voltage is Vt, and this magnitude of this voltage Vt is 1.0, while this magnitude of V is 1.0 and delta 1 is taken as, or delta is 0, the delta 1 is 0. Okay, I can call it delta. Now, with this information or with this equivalent circuit, what we do is we find out what is the phase angle of this Vt with respect to infinite bus voltage. This can be obtained simply by using the relationship that the power output P can be written as Vt magnitude into V divided by the reactance connecting the terminal voltage or terminal of the generator to the infinite bus. And let us say that the phase angle between Vt and infinite bus voltage is alpha. Now, we substitute the values of power because it is we are supplying 1 per unit power. Vt magnitude is given as 1, this is 1, and the reactance between the infinite bus voltage and the generator terminal is how much? 0.3 sin delta, because here we are substituting only the reactance value, it is not impedance, it is a magnitude. Okay. Therefore, with this you can calculate the value of, I am sorry, there is mistake here, this will be called alpha. Alpha comes out to be equal to, is calculated, and alpha in this case comes out to be equal to 17.458 degrees. Okay. Therefore, I can say here that the terminal voltage Vt is equal to 1.0 angle 17.458 per unit. Okay. Now, using this information, we find out the current supplied by the generator. For I can be written as Vt minus V, they are all phasors, divided by the total reactance between the two machines or impedance. The impedance here is how much? J times 0.3. Okay. Now, if you substitute the value of Vt and V, the current comes out to be equal to 1.012 angle 8.729 degrees. Okay. Now, once you get the current I supplied by the generator, we can find out now the internal voltage E prime. That is, E prime can be written as V t plus J times X d into I. Okay? And you substitute the value of V t, X d and I, the calculated value of E prime comes out to be equal to that is magnitude of E prime, because at this stage I am not interested in phase angle right now. E prime comes out to be equal to 1.05 per unit, and the pre-fault power angle characteristic PE1 becomes now 1.05 into 1 divided by total reactance between infinite bus voltage and internal voltage, that is coming out to be how much? 0.5 sin delta here now, because when we are talking in terms of the relation with the power considering the terminal voltage of the machine, we are written alpha. Now delta is the angle, and therefore the pre-fault power angle characteristic is now 2.10 sin. Okay. These steps are extremely important. We will follow, we may have to follow the similar steps for a multi-machine system also. The next step is we want to find out the power angle curve or power angle characteristic when fault is on. When the fault is on the system, we can write down or we can again draw the reactance diagram. Since I have considered the fault at the middle of the line, therefore I will divide this line reactance into two parts and show as 0.2, 0.2 on both the sides of the faulted point. Or fault is at the point P. Now since we have considered a balanced three phase fault, this P will be connected to the reference bus O, directly connected, there is no impedance involved. However, when we consider the unsymmetrical fault, we will see that to analyze the or to obtain the power angle characteristic during fault conditions, there will be some impedance connected between the faulted point P and reference bus. This impedance will depend upon the type of fault, but for a three phase fault the impedance to be connected is 0. Now here we are considering a three phase metallic fault. Okay, there is no fault impedance. Now in this, the total reactance of the these two components, that is the XD prime and the transformer, can be combined, and this can be written as the impedance is 0.3. This is J times 0.4, this is J times 0.2, this is J times 0.3. And this voltage is, this voltage magnitude is, this is V voltage, this is E prime. Okay. Now what we do is, we will try to simplify this network so that we can find out the power angle characteristic during fault on period. This diagram can be redrawn as now we will denote this node as 1, denote this node as 2, okay, this node as 0 and this as. Now, here if you examine this network, then these 3 reactances which are connected in star, J times between 1 and 3, 3 and 2 and 3 and 0. Okay. This star can be replaced by an equivalent delta. The equivalent using the standard star delta transformation technique, this exercise I have obtained, and I find the equivalent network after this star delta transformation as E prime. This reactance comes out to be, when you calculate, it comes out to be, or this impedance comes out to be J times 0.65. This comes out to be J times 0. I am sorry, it is J times 1.3. This is J times 0.266. And what is this value? J times 0.2, and this is your V and this is E prime. Now, these terminals are, this is your 1, this terminal is 2, and the node 3 has been eliminated by star delta transformation, and this is our reference. Now, the power angle characteristic will depend upon the reactance connecting these 2 nodes 1 and 2. 1 is the node of at which E prime is connected, 2 is the node at which the infinite bus voltage is connected. This characteristic is not going to be affected by the shunt branches. Because whatsoever is the current which is flowing through the shunt branches, okay, is not going to affect what is the power which is going to be transferred. And therefore, the power angle characteristic during fault condition can be obtained as, now I will call it as a PE2 equal to 1.05, which is the E prime into 1 divided by the reactance connecting node 1 and 2, and that is 1.3 sin delta. And this comes out to be, they have been computed, and its value comes out to be 0.808 sin delta. Or what you observe here is that this Pe2, which is the equal to P max into sin delta, right. The maximum value of this power angle characteristic will depend primarily upon what is the reactance connecting the internal voltage of the synchronous machine to the infinite bus voltage. More is this reactance, less will be the voltage. Okay. Now, we can very easily obtain the post fault power angle characteristic. Under the post fault condition, one of the transmission line is cleared or it is removed, and therefore, the reactance connecting the two nodes, internal voltage of the synchronous generator and infinite bus voltage, that comes out to be how much? 0.7. Therefore, our characteristic is now this divided by 0.7 sin delta. Okay. Now, these are the three important power angle characteristics which one has to compute or obtain for analyzing the stability of a machine infinite bus system. Either we apply equilibrium criteria or you directly solve the swing equation, it is immaterial. These three characteristics, if you draw, can be shown like this. I will call this as a PE1, the pre-fault power angle characteristic. In this particular case, this is 2.1 P maximum value. Under faulted condition, or the power angle curve under fault condition was found to have the maximum value equal to around 0.808, and therefore, the characteristic can be shown to be like this. And this is 0.808. After the fault is cleared, the amplitude of this power angle characteristic, how much, what is the value of this? 1.5. That is very good. And therefore, the third characteristic can be plotted here. And then this is 1.5, this is your PE 3, this is your PE 2. In some of our representations, what we will do is that the P1 is written as P max sin delta. P2 will be written as R1 times P max sin delta. Okay. And P3 will be written as R2 times P max sin. Okay. Now, this R1 and R2, these are the multiplying factors, constants, they will always be less than 1. And now, I shall take these two examples to illustrate how we apply the equilibrium criterion of stability. Now, let us consider the first case where we assume that there is a sustained fault, fault is not cleared. Okay. Now, in this particular case, the diagram shows that this is the output or normal conditions, or you can say pre-fault power angle curve. This is the output when fault is on, this is the during the fault power angle characteristic. The mechanical input line is shown here, PM. The initial operating angle is delta naught, where the pre-fault power angle characteristic intersect this. Now, the moment fault occurs, the operating point shifts from A to B, then it moves from B on this during the fault power angle curve, and as we have seen that when it comes to this point C, right, the accelerating power becomes 0 and it swings beyond this point, and it swings to a point up to say D, which is corresponding to angle delta m. If these two areas become equal, the rotor will swing up to an angle equal to delta m, and then from this point it will start returning back. Why it starts returning back? Because it is now subjected to retardation. Electrical power is more than the, and when it comes back to this A, what will happen? Will it stop here? No, it will continue to move, and ultimately it is going to settle to this point C, because system has some damping, which we have not considered while writing the swing equation. Now, here depending upon actually the power angle curve, in case actually the height of this power angle curve is less, you will find actually that it may have to swing to larger angle to make these two areas equal. Now, maximum swing up to which rotor is going to be subjected to retardation is where the power angle characteristic intersects with the mechanical input line at this point. In case suppose the energy or kinetic energy gained is not returned back when it comes to this point, then suppose the moment it crosses this point, you will find that the machine is again subjected to acceleration, and therefore rotor is going to lose synchronism. Now, this is shown in this diagram, where the situation is slightly shown to be different, where even when the rotor has come to the point E, these two areas are not equal and system may lose synchronism. Now, the third case and the last case which I am discussing here is that we have a situation where we switch off the faulted line or fault is cleared. Now, you start looking at this, there are three power angle curves. This is the mechanical input line. Initially are operating at this point A. The moment fault occurs, you shift to the point B on the during the fault power angle curve. Now, when you are moving on this curve, at this point C at an angle equal to delta C, the fault is cleared. We call this as a fault clearing angle, the angle at which the fault is cleared. Then you will shift from this point now to the post fault power angle curve. That this curve is the post fault output. Again, as you know that since this is the area A1, that is bound by these two angles and this power angle characteristic and mechanical input line. This becomes the accelerating area. From E, it will continue to swing, it come to the point F, and the maximum angle becomes delta m. At this point, we find actually that these two areas are equal, and therefore the maximum swing is up to delta m, and the system will return back. Now, the new stable operating point is now where the post fault power angle characteristic intersects the mechanical input line. That is, in this diagram, this is the new stable operating point. Therefore, the rotor is going to swing around this point, okay, oscillate around this point, and because it has some damping, it will settle to this new condition. Now, with this I will just summarize what we have discussed today. We have established the Equilera criterion of stability. We have also obtained for a two finite machine system an equivalent machine infinite bus system. We have also obtained for a given particular system the pre-fault, during fault and post-fault power angle characteristic. A simple method is, you can say, discussed here, and at the end I have considered the two cases. One is considering a sustained fault and another is the fault cleared after small amount of time, small time. Okay. I conclude my presentation here, and thank you very much.